Hi, as the title might suggest, we're going to cover synchronous counters in this tutorial, and there's going to be an awful lot in this video actually. I think it's going to be a bit of an epic, and we're going to do the design of a synchronous counter. We're going to cover state diagrams, Karnaugh maps, Boolean algebra perhaps. Yeah, there's going to be quite a lot, so hopefully it's going to be useful. I'm not going to use necessarily the easiest example, because I think there's probably lots of easy examples that you're going to find on the internet. But let's consider some sort of light system, and it's got 3 lamps, and so we're going to have a sequence, and you can have a sequence with synchronous counters, and it's really easy to do that for whatever sequence. They don't have to be like a counting sequence. It can be it can look quite apparently random. So we're going to have 3 different states in this, so I'll call that one state 0, state 1 and state 2. And so we've got 3 lamps. They're not going to be traffic lights, it's not going to be like a traffic light system. Maybe I'll have the middle one on first, and then perhaps the top 2, and then maybe the top and bottom. Okay. Now, like I say, with a synchronous counter you can have any sequence you like. Now, I've only got 3 different patterns here, but because I've got 3 lamps and each lamp can have 2 values on or off, I could actually have more. In fact, I could have 2 to the power of 3, so I could have 8 different patterns in my sequence, but I've decided just to have 3. So in fact what I've got a load of unused patterns that I don't want to use, okay, that I don't want to have. And that's going to be significant when we come to do the state diagrams and the truth table. So let's start with the truth table. And so I'm going to do the states here, so state 0, state 1, state 2. So those are my main sequence states. And I'm going to give each one of these lamps a name or an identifier. So I'll call that bottom one C, and that one B, and that one A. Of course, you could call them anything you like, C, B and A. And so in state 0, that one's 0, that's 1, and that's 0, like that. Okay, I'll have 1 for an on. So 0, 1, 0, 0, 1, 0, and then 0, 1, 1, 0, 1, 1, and then 1, 0, 1. Hopefully that's making sense so far. So those 3 states, they form my main sequence. When I say main sequence, it's really the only sequence that I want. However, if you were to build the circuit, you might find that the circuit starts up in another undesirable sequence, like say, off, 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 or maybe all on, or whatever. Now there are ways around that, but just for the moment we'll assume that it could start up in one of the undesired states. So what are the undesired states? Well, the undesired states are any of the number combinations we haven't used so far, like 0, 0, 0. And when I fill out the undesired states, I always start with the smallest number first, and then I count, and then if I come across a number which isn't yet one in the main sequence, then I'll write it down here. So as I can see, there's no 0, 0, 0, so I'll have that. And then so counting in binary after 0, 0, 0 would be 0, 0, 1. In fact, what I'll just quickly do, so that's state 2, so state 3, state 4, state 5, state 6 and state 7, because remember we've got 8 states, 0 to 7. So 0, 0, 0, 0, 0, 1 isn't being used, so it's not in the main sequence, so 0, 0, 1. 0, 1, 0 is here, 0, 1, 1 is next, that's here, 1, 0, 0 isn't listed at the moment, so 1, 0, 0. 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, so these are my unwanted states. So if I were to start my circuit up and I were to be in an unwanted state, I would want to join the main sequence. Now, in this table now, what we need to do, we need to identify the next states. So these are the outputs here, the C, B and A, and the next states will be the inputs. When we develop the logic circuit, you'll understand why these are inputs and why I'm going to name them data C, data B and data A. Just for the moment, just take it for granted that's what we're going to call them. So if, for example, we are currently in the state 0 and we have 0, 1, 0, the next state, the inputs that will be loaded in the next sequence would be this. Okay, so in other words, we're going to these will take us to the next state. So the inputs will have to be 0, 1, 1. I'm getting them from here. Okay. If I'm currently 0, 1, 1, then I would want loaded next 1, 0, 1. And if I'm currently 1, 0, 1, because I'm in state 2, the next state would be 0, 1, 0, because remember we are in a loop here. Okay, so 0, 1, 0. If, on the other hand, we were to start the circuit up, power it up, and we were to be in one of these states, we would want to join the main sequence. We might join the main sequence directly, so for example if we were at 1, 1, 1 we might go straight to 0, 1, 0, but on the other hand we might go from state 7 to 6 to 3 to state 1 or whatever, it doesn't matter. Okay, so these are not important, or in other words they are don't cares. Okay. And it's important that we put them with an X like that. You're going to understand why. Because in a Karnaugh map, normally we've got zeros and ones, but we also are going to have X's as well this time around. It might, although we can't actually draw a completed state diagram at the moment, it might be useful just to draw a state diagram. And we can always add to it later, and maybe you can understand better what the current main sequence is. So state 0 will be 0, 1, 0, and then that moves on to state 1, which is 0, 1, 1, and then that moves on to state 2, which is 1, 0, 1, and then state 2 goes to 0, 1, 0, which is state 0, like that. Okay, so that's the main sequence. And of course we're going to have, ultimately we're going to have these other states listed somewhere in our state diagram. But at the moment we don't know quite how they work. Okay. Next thing then, Karnaugh maps. And I'm going to do DC first, so I need to find out what DC is in terms of CPA. Well, to do that, I'm going to have my Karnaugh map with C on the left-hand side. C has two possible states, so 0 or 1. And then, so we've got C, and then we're going to have B and A. And BA could be 0, 0, could be 0, 1, could be 1, 1, could be 1, 0. Now, if you're not familiar with Karnaugh maps, you may think that I've made a mistake there, but I'm not counting in binary. Okay, I'm only changing one bit at a time. Right, next thing then, I need to populate the Karnaugh map. And remember this is for DC, so what I need to say is 0, 1, 0, so 0, 1, 0, which is this cell. DC is currently 0. And then what do we got? 0, 1, 1, so 0, 1, 1, which is this cell here. It's going to be 1, and then 1, 0, 1, so 1, 0, 1, which is this cell, DC is 0, and then all the others, if we would fill this out, like for example 0, 0, 0, that's an X, 0, 0, 1, so 0, 0, 1, that's an X, and all of those are X's. Okay, they don't matters. Now, normally when you have a Karnaugh map, you've just got it filled with zeros and ones, and then you try and find the largest groups. You can find a group of, say, 1 or a 2 or a 4, or even an 8 actually. But with the not just having ones and zeros, with x's, we can choose whether we want this x to be a 0 or a 1. So if, for example, you were to use this Karnaugh map and identify that there's only a group of 1, 1, it would actually be not C and B and A, so it would be just a group of 1. However, you can make that simpler by saying, oh, I want that as a group of 2 because this one is a don't care, so I can make that, if I want, I can make that into a 1. So that makes that group actually simpler, because now that's going to be B and A. Remember, BA, that's BA. So we can now say that DA equals B and A. Now we're going to do DB. So DB, we're going to have to work that one out, and so we do the same Karnaugh map again. So C is 0 or 1, and then we've got 0, 0, 0, 1, 1, 1, 1, 0. And that's the B and A. And so DB, we got 0, 1, 0, so 0, 1, 0, that's a 1. And then we've got 0, 1, 1, so 0, 1, 1 is a 0. And then 1, 0, 1, so 1, 0, 1, there, DB is 1. And then if we would fill these out, you'd actually find that they're all don't cares. Now, once again, we've got to find the largest groups that we can to keep it simple. And you might be struggling now, however, bearing in mind that you can change this to a 1, change that to a 1 if you wanted, so you could get a group of 2, but actually you could change that to a 1 and that to a 1 and that to a 1, so that then means that you've got a group of 4 there. And in fact, if you change that to a 1, you've got a group that sort of wraps around there, so those two join with those two, so that's 2 groups of 4. So that group is, and you have to look to see what's not changing here. Well, what's not changing? The not A is not changing, so that's a not A. And then this group, what's not changing? Well, the A changes because here it's A and there it's not A, but the not B is the same on both sides, so that's a not B. So now we can say DB equals not B, or the other group, which is not A. Right, we're getting there, aren't we? It is a bit of an epic video though. So now DA, by the way, if you find the videos useful, please do give it a thumbs up. So DA, and we're going to do the Karnaugh map again, 0 and 1, and we'll have B and A, which can be 0, 0, 0, 1, 1, 1 or 1, 0. And so, what do we got? 0, 1, 0. So 0, 1, 0, DA is 1. And what else do we have? So 0, 1, 1. So 0, 1, 1, that's a 1. And then we've got 1, 0, 1, 1, 0, 1, which is there, and that's a 0. And all the others, I don't cares. Now, you've got a choice this time. You could have a group of 4 here, in which case that would be B. Or you could have this row here, that group of 4. It doesn't make any difference. I'm going to have that group of 4, and that group of 4 is not C. Okay? It's up to you which one you choose. Now, I say that, but when you actually draw the state diagram, you might find that one of them has stuck states, one of them doesn't, so you might have to go back. But for the moment, I'm going to go for not C. So now that we've got these, we're ready for the next stage, which is applying these to the don't cares, doesn't matter, whatever you want to call them, and then we can populate those, so then we'll know that if we're currently 0, 0, 0, what will the next state be. So DC is what we've got to fill out this DC column. And so DC is only going to be true when B and A is true. So B and A, we got B and A, no, so that's 0, B and A, no, B and A, no, no, but that is true, okay. And then we've got a not B or not A, so that's for DB. So a not B, well not 0 is 1, that's 1, that's 1. And not A, that makes it 1, and then that makes it 0. Okay. Hopefully you're following this. DA is quite simple, not C, so we're just going to have complement C. So not 0 is 1, not 0 is 1, not 1 is 0, 0 and 0. Okay. Now we now have the next states. So if, for example, we are in state 3, when we power up, state 3 is 0, 0, 0, we go to state 0, 1, 1. Actually, I can see that there. That was quite easy to spot. So that's going to be state 3. If we start in state 3, which is 0, 0, 0, it would progress to 0, 1, 1. Okay. And if we're in fact, state 4, it will go to 0, 1, 1 as well. So if we're in 0, 0, 1, it will go to 0, 1, 1. And if we're in 1, 0, 0, it will go to 0, 1, 0. Do we have that? 0, 1, 0. So state 5, which is 1, 0, 0, that's going to go to state 0. What have we got next? State 6 will go to 0, 1, 0 as well. So state 6 is 1, 1, 0, and that will go there. And if we're in state 7, which is 1, 1, 1, it will go to 1, 0, 0. Where is that? There, okay. So if we're in state 7, it actually requires 2 hops then. It's going to go from 1, 1, 1. It will then go to 1, 0, 0 on the next clock pulse, and then on the next clock pulse it joins the main sequence. Remember, these ones, these 3 are the main sequence. Everything else is undesired or unwanted states. Cool, right, okay, so hopefully that makes sense. The next stage then is to make, using these, is to make the synchronous counter using D-type flip-flops. I'm just going to pause this video, grab a drink, and then we do the next part. Okay, hopefully you're still watching, and I'm going to now use these to make the synchronous counter. And we're going to do it with D-type flip-flops. And the D-type flip-flop has a clock input, that's the clock, and it's got data, it's got an output, the output is Q, and each one has an output Q, and then they have the complement of Q or the not Q as an output as well. Now they can also have set and reset, just to keep things simple. I'm not going to put the sets and resets in. The clock, because it's a synchronous counter, is going to be fed into each of the D-types, so it's synchronous, it's going to be clocked at the same time. Now each one of these is going to represent our A, B and C. It doesn't really matter what the order is, but let's say that's DC, that's DB, and that's DA, so that's the data input for C, and the data input for B, and data input for A. And so that's going to be Q, C, Q, B, and Q, A, and of course that's going to be the C, B, and that's going to be the A. Right, okay, so we're going to have the outputs. And the outputs would be connected to our lamps, okay? Right, that's the clock. So on each clock pulse it's going to go to whatever is the next thing in the sequence. So that's going to be my A output, that's going to be my B output, and that's going to be my C output lamp. Okay. Right, now each one of these is going to have an input, and let's just grab a pencil. I might want to raise this later, depends on whether it confuses you, but on the clock pulse whatever is at DC will be loaded into QC, so there's a transfer of data on the clock pulse. Okay. On the rising edge, okay, it's an edge triggered device, right? Okay, so so DC is going to be B and A, so all we need to do there, got a logic gate, okay, and it's got two inputs, and one of those inputs is going to be tied to B. This is going to get scruffy, I tell you. It's quite important. If you're one of my students, by the way, do put the dot, show that there's a connector, because you know if there's no dot there's no connection. Alright, so that is B, and then we also want to connect it to A. This is going to look terrible, but yeah, let's go around here. Okay, so A and B, B and A. Alright, so that's that first one. And then DB is going to be, there's going to be an OR gate. Now, don't make the mistake of doing NOT gates, because you can get the complement of B from the Q bar. Okay, and same for the A. So let's do that. So that was the NOT A, and then we can also get the NOT B, like so. Okay, right, and then so DA is going to be NOT C. So oh, this is going to look ugly. However, can't be helped. Okay, and that okay, that is oh, get that right. That's not C. Okay. Right, that is the synchronous counter, and if you were to test it, you would find that if it were to start by chance, because it would be by chance if it started with 0, 1, 0, it would then progress to 0, 1, 1, and then 1, 0, 1, and then it would go to 0, 1, 0 and go on. Oops, sorry. Go on forever. If on the other hand, say it were to randomly start at say 0, 1, 0, 0 for example, then the next state will be 0, 1, 0, sorry, 0, 1, 0, and yeah, so yeah. Hopefully that makes some sense. Hopefully it's useful. The only way we would prove that this would work would be if we were to maybe simulate it, and I think that's just going to make the video a little bit too long. So I do hope you found this useful. Hopefully you managed to follow along. If you've got Circuit Wizard, maybe you want to even try building this circuit, and yeah, so please do give it a thumbs up, like and subscribe if you want to. Would much appreciate it. Okay, that's it for now. Thank you, goodbye.